Welcome in the AI for You Cafe with Hannes Fassold, who is our speaker today, and I'm very happy you see him already. Hi, Hannes. Yes, he will present to us his talk, Employing AI for the Semantic Analysis of Conventional and Immersive Video. My name is Carl McWilliams. I'm the moderator and organizer of the cafe. This is now our 60th cafe. So thank you that you're all coming. Welcome today. Please take notice that this session will be recorded. No confidential information shall be shared in this cafe session. In this cafe, the speaker expresses his personal view and opinion. This is not necessarily the official AI for You or AI for Media project opinion. And what is the cafe about? It's an online forum to gain insight in the European AI scene. And here participants get the chance to share knowledge and experiences, meet stakeholders from various areas of AI research and application. As you know, who has been here, this is interactive. We live off your questions, so please, we're looking forward for your questions. You can type them during the presentation into the chat board. It's on the right side of the menu. There's chat and questions. You can just type them in. I'm sorry, we cannot take hand signs. We cannot take voices or speech as we have so little time and so many people are here in the cafe. So please type them in. I'm going to write them afterwards. I'm going to read them afterwards to the speaker. Thank you. Yeah, now we come to the main attraction. It's not me, it's Hannes Fassold. He is the senior researcher at the Machine Vision Applications Group of the Digital Institute of Joanneum Research in Austria. So I'm going to read the small bio. Hannes Fassold received a master's degree in applied mathematics from Graz University of Technology 2004. And he works at Joanneum Research, where he is currently a senior researcher at the Machine Vision Application Group of the Digital Institute. His main research interests are the automatic analysis and enhancement of video. For example, object detection and tracking, optical flow, speaker recognition, defect detection, super resolution, denoising, with deep learning methods. He has published several publications in these fields and coordinates the machine learning workflow infrastructure at Digital. So now, after my introduction, again, I welcome you. Hi, Hannes.
Hello.
And hi. I'm giving you now the floor, the moderator role, and then you can show the presentation as well as introduce yourself, which is probably much better. And now I give you the moderator role, and yes, I already see your PowerPoint.
All right, so welcome all to this kitchen session. So my topic is about employing AI for the semantic analysis of conventional and immersive video. So I'm a senior researcher at Joanneum Research Digital. So who are we? I'm in the smart media solution team. So it's a team in the I just put away. Do you see the comment? The go to webinar windows you can see, or no?
I only see you.
Yeah. Okay. Yeah. I see them. I will shift them down. So we are in the Machine Vision Application Research Group at the Digital Institute of the Joanneum Research in Graz in Austria. So Joanneum Research is an applied research institution. So our team is doing a lot of computer vision stuff, focusing on several areas. The first one is on a content-based video quality analysis and video and film restoration. So here we have our own product, which is called Video Search, and for quality check of video. And we are also providing restoration algorithms for a software called Diamant Film, which is sold by our partner, company partner, HS Art. Yeah, and the other thing we are doing a lot of stuff is on semantic video analysis. So here we are extracting semantic information, so high-level, low, mid, and high-level information from a video or film with classical methods and also all sort of deep learning or AI methods. For example, we have here components for shot and cadence detection. So cadence is whether it's interlaced or progressive or pull down and so on. Then we have powerful components for object detection, recognition, and tracking. So like for detection of faces, persons, and logos. I will give more on that later on. Then on speaking person detection. And we have also components for similarity matching of images and also video segments using efficient compact descriptors. And we have been heavily involved there in the standardization of that into the MPEG CDWA standard. And yeah, most of our components are real-time capable. Okay, so a short overview about the presentation. So first I will give a sort of a crash course into deep learning and AI. Then I will present some information on face detection and recognition, about the state of the art and also remaining issues. Then the same for object detection and tracking, so state of the art and also the issues there. And then I will give some information about applications of these algorithms. And there are two I will present two. Of course, there are a lot of applications. The first one is about semi-automatic annotation of video, and the second one is about generating a non-interactive version of 360 videos, a sort of a automatic cinematography or doing a automated editing of a 360 video. So the basic terms and definitions in deep learning are, I will give some information on that. First of all these deep neural networks, so DNNs, you can see one at the right, at the figure to the right, and they're sort of mimicking the human brain structure with all these neurons and synapses and so the cells and the connections. And you can see that on the right, and also what one can see is that there are a lot of layers. So the input layers at the left side, where, for example, some image comes in, and then there are a lot of hidden layers with a lot of connections, and then there is the output, so the result of the algorithm. And these layers can be interpreted in some ways. So actually the first few layers, they in such a visual system, they are encoding so very low-level information like edges or corners in the image. And then in the medium layers, which you can see here in the middle, you have also a higher level information, like for example, parts of an object. And then in the highest level, in the highest layers, which are to the right, you can see they are encoding already very high level information, like the full faces and so on for a face recognition system. Yeah, then there are these terms like training and inference. So what is training? During training, you are learning how to connect these neural network, this artificial neural network. So you are learning the weights for layers or sort of the connection strengths between all these layers. And for that, you need a huge annotated data set for training from scratch, so from zero. Annotated means you have to label the data. For example, for a face recognition system, you have to give for each face the name of the name of the person, which yeah, or for object detection system, you have to draw in the location of the objects and the classes. Yeah, then there is inference, and inference is simply you are running the network, and which does a certain task like classify or detect or whatever it's trained on. And you run this network for one input, like for example for one image. And both the training and the inference, they are usually done on graphic cards or GPUs because they are much more powerful than CPUs. So what are now the most useful or most popular neural network architectures? There is first of all the convolutional neural network, so CNN, and these CNNs, they are very often used in computer vision for many tasks like detection or segmentation. You can see the segmentation result to the right for a street scene, or for action recognition, so what is a person doing in a video, or for pose estimation, where you are fitting sort of a skeleton into a human body. You can see that also to the right. Then the generative adversarial networks, so the GANs, they are also very popular, especially for image synthesis and for image transformation or style transfer. So these are quite famous, these GANs, for all these deep fakes or synthetic faces. For example, the two faces here to the right, they do not belong to any human being. They are completely synthetic, but photorealistic, so you couldn't say whether this is a real person or not, and these are not real persons. Then for example, style transfer, like photo to convert a photo to a cartoon or to a sort of a painting. So these are the applications for GANs. And then there are the transformer architectures. These are not for images, so for computer vision, but for text processing. They are very popular there for NLP. This is natural language processing. And here, they are used for all sorts, for all kind of text-related tasks, like language translation or text summarization or entity extraction. Entity extraction is very useful. It extracts from a text all names, all places, all dates. So for example, to the right, you can see such an example for entity extraction. Okay, so let's move forward to face detection. In face detection, the state-of-the-art approaches here are, I've named a few recent ones, which are multitask, CNN, retina face, and TINA face. And there are a couple of more, of course. This problem is more or less solved, I would say. So it works really great, even for small faces, and also for profile views of faces. For example, as you can see in the photo to the lower right, the faces here are really very small, and so just, I don't know, a couple of pixels or so, and they are detected really reliably. In terms of accuracy, you get an accuracy. So there is this score called MAP, mean average precision, and you get an accuracy of more than 95% for easy and medium examples, and still more than 90% for hard examples, so like small faces and so on. And the approaches, they are processing in real time on a GPU. So what about face recognition? So here you want face recognition means you want to know which person this face is, not only detect the rectangle around the face. So here, here state-of-the-art approaches are here. FaceNet is a classical approach. Arc face and spheres face, and you have here an accuracy of more than 98% on the standard databases, and it's also processing in real time. One constraint of these algorithms, or on most of the algorithms, is that they rely on the so-called closed world assumption. So that means all faces which occur in the video are known. So the face recognition algorithm has been trained on them. Of course, that's a bit of not that practical sometimes, but most algorithms rely on this assumption. And for face recognition, yeah, there are more or less the same factors which influence the or which worsen the recognition result. So of course, if you have a small face or a low resolution video, then the face recognition will perform not that good anymore. Also, profile view is more difficult for a face recognition algorithm. Also the lighting, if the lighting is bad. And yeah, the fourth thing is in these times, of course, if you're wearing your masks or corona masks, of course, this influences also, this worsens also the recognition. Yeah, so as I mentioned, this closed world assumption is actually difficult to achieve in practice because your face database, there will be always new people you want to recognize also, and you don't want to retrain your whole neural network because the training it takes quite some time. So the so-called incremental training can help there, so that you're just you're performing sort of a fast retraining with the new faces with the new persons you want to add to your database. This is actually not an easy task, as we have seen, because you have first to identify that the person is not in the database, and then you have to retrain the neural network on the fly. We have done that, and we have added here an incremental training component in our face framework, in-house framework. So we have a face recognition pipeline in-house. Yeah, and the other thing is you may not have enough annotations or samples for each person. In these face recognition databases, usually for each person you have maybe 50 to 100 labels or face images, and that's quite a lot, and often you don't have that much for a person. So the training with less data is also an active research area, and it's called few-shot learning. Yeah. What are some other challenges and issues? Yeah, one issue is the class imbalance. So some of the classes are not that good represented in the data set used for training the DNM. And another issue is the ethnic bias. So most face recognition algorithms are training on these public face data sets, and they contain mostly faces from Caucasian people. So what some people have found out is that, for example, for African people, the error rates are about twice as big as for Caucasian people. And yeah, that's of course really a problem. Yeah, another thing is that in these face data sets, there are not that much faces with glasses, but many Asians have glasses, and that also worsens the performance of a face recognition algorithm. Yeah, and there is active research on methods how to mitigate these class imbalance and to mitigate these all sorts of biases. You can employ better data augmentation strategies. You can rely on data crawling, so getting more data from web sources and so on. You can synthetically generate additional training data samples, for example, faces with glasses, by transforming existing images or synthesizing new samples. And yeah, there is the wide area of semi-self or unsupervised learning. So that's learning without having annotations or labels, or just having, I don't know, a few samples, a few annotations. All right, so let's move on to object detection and tracking. So here is the task to an object detector and tracker detects an object of a certain class, for example, like a person or some animal or a car or a bicycle, and then tracks it in the video as long as it is visible in the video. So each object here gets an unique ID. You can see here a result on the figure to the right. Here the state-of-the-art approaches are called RetinaNet. Then YOLO FAR3 and FAR4 is very popular. We use it extensively. And there is faster RCNN and a lot more. So there is a vast, a very huge amount on papers and publications for object detection. Most approaches detect the 80 classes from the MS-COCA dataset. So these are 80 object categories or object classes. Yeah, and our in-house, we have here an in-house algorithm also relying on YOLO for the object detection. And it's able to detect and track general objects and also faces and text and logo in real time. And I will show now a demo video how that looks like. So here, these are the 80 classes from the MS-COCA dataset, like person or backpack, and this is another neural network which is trained only on face detection, so it only detects and tracks faces, but with very good performance. And this is another network which has 500 object classes, so also object classes like building or plant, or also I think for shoes or so. One thing is, the more object classes you have, then the more difficult is it for the network. So network detection performance goes down actually, yeah, for these 500 object classes with the latest neural network. So what's the state of the art and the issues here? The algorithms for object detection and tracking, so you can really use them for applications. They are robust and also fast. So you can get real-time performance, and you have detection performance currently, which is about 65%, and that's really enough to do a lot of nice applications, yeah, to use them in a lot of nice applications. Of course, there are some issues still left. One of them is that the re-identification of objects is a problem still. So, for example, if you have a person which gets occluded and then it appears again, like you saw in the demo video when you have a crowd, then the person gets a new ID. So for the object detection algorithm, it's not the same person anymore, and that's a problem in certain applications. So we have added here in our framework a specialized component for person re-identification, only for persons. It uses, of course, also deep learning methods, and that seems to work quite nice. But of course, you have always corner cases. For example, if these re-identification algorithms, they rely on the appearance of the object. But if all objects look, for example, if all persons look the same, like in a soccer team or so, you have a problem. You can't easily distinguish them. Yeah, and the other problem is, that's also a major problem, I would say, is that the number of object classes is quite limited. So for example, this MS COCO dataset, it has these 80 classes. For example, for animals, I think it has 5 or 6 classes, like dog, cat, horse, cow, and sheep, I think. But if you want to track something and detect some other animals, like a dinosaur or whatever else, you have a problem because it won't get detected in the video or image. That's a real problem. That's maybe even more of a problem than the detection rate currently. And here we are also working in the AI for Media project on few shot object detection components, which are able to learn to detect a new object only from a few samples. Yeah, so we are working on that, but we have nothing ready. Then we go to the first application, which is the of these algorithms, which is semi-automatic video annotation. So here the task is to automate the annotation process of broadcaster archive videos, for example. You want to know who is appearing in the video and with whom, and in which video section the person does appear. Of course, there would be more useful metadata, like detecting the motion of the person from the face, or detecting what action the person is doing, what is he saying, which logos appear, or what are the video highlights. Yeah? That would be also useful metadata, of course. So for the semi-automatic video annotation workflow, one could think of a pipeline where first the deep learning-based algorithms for face recognition and object detection and tracking, and possibly other components, process the video in a first pass and generate a sort of raw metadata. And this raw metadata is then inspected and corrected by a human operator with a convenient tool. So you have sort of a human in the loop. Yeah, the human is correcting errors the algorithms are making, like false detections and stuff like that. Yeah, and the hope would be here that this semi-automatic annotation workflow is more time efficient, more efficient than the human-only workflow. Okay, so the second and final application I want to show you is automatic cinematography and editing of a 360 video. So here the task is to generate you have as input a 360 video, and you want to generate a normal 2D version of this 360 video, yeah, which can be played out on a normal TV. So you have shots and you have hard cuts between and so on. This could be useful for two things. First of all, you could generate sort of a preview version of the 360 video, which you could put them into the archive just for quick inspection of the video. And the other use case would be if you want to consume the 360 video on an old TV set, which does not have a 360 player, or you could use it as a lean back mode for users who do not want to interact. So they just want to see where in the 360 video currently the sort of the action is happening. You can see an example at the right here. Here on the top image is the 360 video itself. This is in equirectangular projection. And then you see for the first 4 shots of the generated 2D video, or of the generated classical video. And for each shot, you see 2 frames. Yeah, and these we have implemented here a prototype for such a prototype algorithm, and it employs deep learning based methods for extracting the scene information. Specifically, it relies on object detection and tracking with Viola 3. We are detecting the face and also the 80 MS Coco classes. So especially we are focusing on persons. And we are doing also a human pose estimation. So we are fitting a skeleton into each human body appearing on the screen. And this is used for checking whether a person is looking frontally into the camera or not. Yeah, and the algorithm outline in a high-level view is the following. So it works shot by shot in an iterative way, and each shot is about 3 seconds, but that can be parameterized. And yeah, you are extracting all the objects in the scene and tracking them with our object detector. And for each detected object, we are now calculating certain measures, which is, for example, the average size of the object, the average motion magnitude, so how much is it moving in the scene. Then also, yeah, sort of how isolated the object is within its neighborhood. So are in its neighborhood objects of the same class or not? And then we have a sort of a visited measure, which tells us how often a certain area of the 360 video has been already visited in the generated 2D video. Yeah, so we are calculating the scene object measures, and then we have different shot types. We have a tracking shot, a static shot, medium shot, pan shot, and so-called recommender shot. And these are shot types which are coming from classical editing and filmmaking. For example, a tracking shot tracks a certain object throughout the scene, throughout the video. Or a pan shot, it's just a horizontal pan with a fixed speed, which is more for exploring the scenery. Yeah, so each shot type has a different characteristic and a different artistic purpose. So they have a different field of view, different camera motion. Also, the focus object is different, and so on. And then for each shot type, we are generating a few shot candidates. And for each of these shot candidates, we are calculating a score, sort of how interesting this shot would be for the viewer. And then we are picking the best shot candidate, and we are rendering the frames. Yeah, so that's the workflow. I will show now a demo video, unfortunately without sound. So this is now the generated 2D video from a 360 video. and it's generated completely automatically. So this is a static shot. This is a pan shot. This is a tracking shot, I think. This is a medium shot. This is a tracking shot again. Pan shot. Okay, I think you got a feeling how this prototype performs. So yeah, actually a result looks quite nice, and yeah, and it's you can apply it for also for other 360 videos, of course, not only for these sort of concert videos. Okay. Yeah, so thanks to the Hyper 360 project partners, especially RBB and Mediaset for providing these 360 video sequences for R&D. Yeah, this work has been done in these two Horizon 2020 projects in Hyper 360 and AI for media. All right, so come on, that's it from my side.
Right.
So you can put away the screen share if you want.
Yes. And as time is running, Esma, thank you very much for
you're welcome.
insight into employing AI for semantic analysis. And I just have a few questions here, and I would like to read them because we are getting late. And the first one, basically, let me just, I just lost it because it was here. One moment, I got myself confused. Are you collaborating with startups? That's from Sachin Gauer. Are you collaborating with startups? Also, if you can illustrate the use cases where your work can be practically applied?
So yeah, we are collaborating, difficult word, with startups, yeah, quite frequently in the course of various European Union research projects. So here we have usually the research partners like us or other university, and then we have user partners which often are SMEs or startups, and which are then disseminating and exploiting the generated so our prototypes. So okay. Yes, we are doing, yeah.
So, and then second question of Sachin, and then from a known set of faces. So we're going back to the face recognition.
Yeah.
Known set of faces. When we get an unknown person, can we reliably give an alert of unknown person use case?
Yeah, of course, because that's, yeah, I think I have still the screen, or
yes.
Yeah,
complete the moderator.
Because that's that's a crucial component of incremental training, that you identify first that the person is not in the current database. So that's yeah, you can. Yes, you can, but it's we had quite a I was not involved there personally, but from my colleagues I know that it was quite a tough thing to identify a new person in a robust way.
Okay, but that would be, for example, a good example, no? For an SME
Yeah.
collaborating. That's from this. My Sachin is probably asking that because that would be a good thing, no?
Yeah. Actually, our face recognition framework is already in use by several user partners, which are one is an SME, I think. Yeah.
Okay. Now, new question. Sonia Afrikasis. She asked, so nowadays, would the state of the art recognize young Michelle Obama?
I'm afraid I don't get the question. What you mean you have Michelle Obama in the photos of her in her nowadays, and you want to recognize her 20 years ago or something as a teenager. Yes, there are, but not by default, I would say. So most of the face recognition algorithms, they won't perform that well. They won't recognize her. Maybe they will, but not that reliably. But there are a few face recognition algorithms in the literature which are sort of age invariant, or which are able to recognize a person's face throughout maybe I don't know 40 or 50 years or so. So there are approaches which are able to do that, but they are sort of a bit of a niche in the literature, in all these academic works. So there are some which do this, but they are quite a bit special still.
Yeah. So now comes my question, because I did already 20 years ago research with Johan. So I don't think you were there 20 years ago, but we had cases with the ORF. We wanted to do the live Olympic Games in real time. We broadcasted in several streams interactively, so people could switch between the channels. And the idea was to, in real time, get, of course, the sport people, no? Where they are. Is it, I mean, at that time it was so-so. How is it today? You think in real time, when there's like several, all these different streams coming from the Olympic Games, could you now reliably, find in the different streams the sport people?
So you mean all the players or athletes and so on, yeah, in various sports, in various games. Yeah. I think you can do, and you can do it in real time, and you can do it even with several streams with compact neural networks, and you can do it quite reliably. Maybe for a bit more would be a bit more difficult for sports where the athletes are, I don't know, moving very quickly, or there's fast camera motion and motion blur and so on, and maybe the athletes very small, but
mainly, yes.
yeah. But
Yeah.
yeah. Generally, I would say you can do that quite robust.
Yes, because also, of course, sport people can be, you can train it before, no? I mean, they're known, no? So,
Yeah. You can you could sort of specialize the network for a certain sport, yeah, by recording videos and annotating them, yeah.
yes.
But
And
even
then,
out of the box with a general person detector and tracker, it would take you quite a long way. So it would be a quite nice default approach, I would say, yeah, which works nice. Yeah.
yes. Okay, thank you. We are coming soon to an end. So last question here. That is maybe a little bit already answered, but anyway, what is with the people who grow beards? And I mean, you know them, but then they grow beards and shave and yeah, put other things in their face. Can you still recognize them?
That's a good question. Ooh. I might have to pass on that. My feeling is you could have the face recognition algorithm could have a tough time. So it could fail very easily, especially for a full beard. Not only I don't know, from the sides or on the chin. Just because also for a human it's very, for me it's difficult if there is this person's face and then you have the same person's face with a full beard. It looks so different. So and the general line is, if it's difficult, or a good baseline is, if it's difficult for a human, then it's also difficult for an algorithm. There are some exceptions to that where an AI algorithm is able to do better, even much better, but that's a good baseline, I think, yeah.
So a tip,
So,
if you still want to hide from video face recognition, grow a beard.
yeah.
Okay, no, but thank you. We are like shortly before the end of today's cafe, and as we always know, if you have more questions for Hannes, you can email him.
Just contact me, yeah.
And at your name also, if you want to basically get the recording, it's always the same. I will first send the recording to Hannes, to the speaker. You, Hannes, can then say, yes, no, I publish. And then after that, you may or may not publish it on YouTube and in our AI for You channel, basically on YouTube. And then if all is positive, then I can send you the recording link to the participants.
Yeah. It's I told her already, Carmen, it's a bit difficult, mainly because of the demo videos in the presentation. So the presentation would not be a problem. I don't know if you have can do a sort of cut recording where you have cut out the demo videos. It could work, yeah.
Yeah, I think I keep it on the GoToWebinar archive. I think it's better, no? And because we don't edit really the internal content, I keep it on the GoToWebinar, and we are not going on YouTube. I think it's better, no?
Yeah,
we just in our, here in the AI archive for the research partners, and that's it.
Yeah.
I think it's better.
That's fine. I think, yeah.
It's better.
Hmm?
Still, I sent you, Hannes, the recording, so you see what's in the archive here. You can even say, I don't want to be in the archive from the AI for You. Then
no, it's fine for me.
Okay. Yeah, then I just gladly invite you for next week, and you will get invitations. So be ready. And it's basically, we have next week, we have Olga Hamama. She is a lawyer, and she will have a talk on use AI policy and regulation. How can SMEs and startups test the trustworthiness of the AI application? So it's a hand-on webinar, maybe really more for all the entrepreneurs out there who want to be entrepreneurs, because we often get these kind of regulations and ideas, what is trustworthy AI, but how can I really test it? How can I find out if my AI application is trustworthy? So that's next week, and I hope you all come back. And thank you, Hannes, and have a nice
You're
day.
welcome. Yeah,
Bye-bye.
thank you. You too.
Bye-bye.
Bye.